Okay, hi guys, so let's continue with seeing on the calculation of Kp and Kc values. So let's get started with another example. So suppose we have this reaction N2G, oops, N2G plus 3 moles of H2G combining to form ammonia, 2 moles of ammonia. So let's say initial moles present in the mixture were A moles of nitrogen and B moles of hydrogen, and moles at equilibrium were, let's say, A minus X. So X moles of nitrogen were consumed in the reaction, so remaining moles of nitrogen at equilibrium would be A minus X. Similarly, if X moles of nitrogen were consumed, 3X moles of hydrogen must have been consumed, so remaining moles of hydrogen at equilibrium would be B minus 3X, and 2X moles would be formed 2x moles of ammonia would be formed at equilibrium. Okay, what would the concentration of the following molecules or compounds at equilibrium? So concentration would be, just divide A minus X with the volume of vessel, B minus 3X again with volume of the vessel, and 2X again with the volume of vessel. And what would be the partial pressure at equilibrium? Partial pressure at equilibrium would be nothing but mole fraction of the respective molecules multiplied with the total pressure of the mixture. So mole fraction, so before that, let's calculate the total moles present in the mixture at equilibrium. Total moles at equilibrium would be nothing but A minus X plus B minus 3X plus 2X. So it would be A plus B minus 4X plus 2X. That would be nothing but A plus B minus 2X as the total moles at equilibrium. Okay, so mole fraction of nitrogen would be A minus X divided by A plus B minus 2X. This is the mole fraction, and if you multiply the mole fraction with total pressure, then please the total pressure, then what happens is we get partial pressure of following compound or molecule. Similarly, it would be mole fraction would be again B minus 3X upon total moles, which is A plus B minus 2X multiplied with partial over total pressure. Similarly, for ammonia, the partial pressure would be 2X divided by A plus B minus 2X multiplied with total pressure. So Kp in this case would be partial pressure of NH3 square divided by partial pressure of nitrogen squared, not squared, its stoichiometric coefficient is only 1, so P to the power 1 would be there, so only P, partial pressure of H2 cube. And Kc would be, okay, so before going into Kc, let us fully define or fully write the value of Kp in this case. So P of NH3 would be 2x divided by A plus B minus 2x into P squared divided by partial pressure of nitrogen would be A minus X divided by A plus B minus 2x into P, and partial pressure of hydrogen would be B minus 3x divided by A plus B minus 2x whole cube and P cube. So you can simplify it. So after simplifying it, we can see that P square would be remaining, because here 1 plus 3 is 4, so power in denominator is 4 and power in numerator is 2, so I am just writing P square in the denominator. Similarly, I can write A plus B minus 2x square in the numerator. Why? Because if we just observe it closely, we can see that the denominator of the denominator goes into the numerator, so numerator would be having A plus B minus 2x to the power 4, A plus B minus 2x to the power 4, and this denominator is A plus B minus 2x to the power square. So just cancelling out 4 with 2, so we get a square in the numerator term of a minus bx, a plus b minus 2x. So this part is done, this is done, p part is done. So next, what is remaining? Only the numerator parts of the corresponding partial pressures. A minus x multiplied with b minus 3x whole cube. Similarly, for Kc, we have concentration of NH3 squared divided by concentration of N2 and concentration of H2 square cube. Concentration of NH3 was 2x by V cube. Concentration of N2 would be moles of N2 present at equilibrium divided by total volume of the solution or the mixture, and H2 would be B minus 2x divided by B minus 3x rather, B minus 3x divided by total volume of solution cube. So on simplifying it, we can see this is square, not cube. Yep, because this is a square. So on simplifying, we'll get 2x square divided by a minus x multiply with v square would be in the numerator term, and then what is left is b minus 3x whole cube. So these two are the Kp and Kc values of the following equation. So let's suppose we have a twist that if in the same problem we say that if C moles of an inert gas is also present, so in that case what will happen? So if C moles of inert gas is also present, then as inert gas will not react with any of the compounds or molecules at equilibrium, will just add it, but it would rather add to total number of moles in the solution. So total number of moles at equilibrium would come out to be nothing but, at equilibrium we already had a minus bx plus c, a plus b minus 2x, and we just have to add c plus c term here. So what parameters will be getting affected? X, which is mole fraction of each individual molecule, will be getting affected. What else would be getting affected? Partial pressure would be getting affected, because partial pressure is dependent on mole fraction. Hence these two quantities will be getting affected. Okay, so coming to the next note, that for ideal gases we can say that volume percentage is equals to mole percentage. And why is this the case? Because for ideal gas, PV equals to nRT. This is the equation which gets followed. Hence we can equate mole to volume. Okay, so let's suppose if you have been given that in the previous example, in the preparation of ammonia, where we reacted N2 with 3 moles of hydrogen to form 2 moles of ammonia. So let's say in that question or in that problem you were given volume percentage of hydrogen at equilibrium as, let's say, any number which is 25. Okay, so you know that PV equals to nRT, and suppose that all the gases in the mixture were real gases, beg your pardon, were ideal gases, means following this equation PV equals to nRT. So at same pressure and temperature condition, V is directly proportional to N. This implies volume percentage would be equals to mole percentage. So we just have to compare, or rather equate the mole percentage of hydrogen with volume percentage. So as these two are equal, we can say that mole percentage of hydrogen would also be equals to 25. Okay, and mole percentage can be calculated as moles of hydrogen divided by moles of total moles in the mixture multiplied with 100. So we have been given that in the previous question moles of hydrogen were B minus 3x and total moles were, after the adding of inert gas, A plus B plus C minus 2x. Just multiply it with 100 and equate this value to 25. Obviously you will be given A, B, C, and you will be asked to find the value of x by giving you the mole percentage as in this case, so it would be easy for you to calculate. So with this we come to the end of this lecture. In the next lecture we will be taking on degree of dissociation. Okay, so this is the second method of the calculation of Kp and Kc in at equilibrium for certain reversible reactions. So till then, good luck and goodbye.